Let's start with our course in classical mechanics. Before we go into the rigorous mathematical proofs and derivations and analytical solutions given in classical mechanics, let's understand what is mechanics initially. So mechanics is that branch of physics which deals with physical objects in motion and at rest under the influence of external and internal interactions. These interactions we will call later as force. And the nature of these forces was initially described by Newton in his famous laws, also known as Newton's laws of motion. Okay, so before we revise these laws of motion one by one, let's understand how different classical mechanics is from the mechanics developed by Newton. Newton's mechanics, also known as Newtonian mechanics, usually deals with vector quantities. The vector quantities like force, momentum, acceleration, and it is also known as vectorial mechanics. While the classical mechanics developed by Lagrange, Hamilton and others mostly take into account scalars. So we will deal mostly with scalars in classical mechanics. We will see how to approach a given problem using scalars. Classical mechanics is a good way of describing the world around us, but it is inadequate while dealing with the behavior of subatomic particles and the systems which are moving with larger velocities comparable to the speed of light. And for systems, microscopic systems, we have quantum mechanics that we will deal maybe in other segment. So before we go further, let's start our course with the famous Newton's laws of motion and check the limits of these famous laws. Let's start with Newton's first law. So according to Newton's first law, an object preserves its state of rest or motion until any force is applied on it. Now the question is, why this object wants to preserve its state? And a direct answer to this question can be inertia. So inertia is the property, or one can say resistance, to change the state of the object. It preserves the state of motion or rest for the object. This resistance to change its state in case of translation motion is due to the mass of the object, and hence the mass is the translational inertia or rectilinear inertia. Mass is also defined as the amount of matter contained in any object. So more will be the mass, you need larger amount of force to change its state. If the mass is less, you need less amount of force to change its state. So this is a very important outcome of Newton's first law, inertia, law of inertia, which states that an object will preserve its state of rest or motion until or unless any external force is applied on it. Now Newton's first law of motion is a qualitative law since it describes the nature of the state of any object, while Newton's second law is a quantitative law which states the amount of force required to produce the acceleration in a given object, which means you are quantifying the things. How much force is required to produce how much acceleration? That will be given by Newton's second law. But before we go into that and derive Newton's second law, let's understand what is momentum.